All right, welcome back to the Professor Carbon channel. In this video, what we're going to do is go over a synthesis problem about how to prepare, or at least how we could think about making, this relatively complicated ether from benzaldehyde. As I've mentioned before, often synthesis problems are probably one of the most difficult problem types that you can get assigned in an Organic 1, Organic 2 class. And the reason for that is you need to not only know your reactions forward, you need to know them backwards, and you have to be able to recognize some common pitfalls of those reactions or some functional group incompatibilities where there might be some hiccups. So I'm going to take a minute here to pause this video and encourage you to try to make an approach to complete this problem in the forward direction. And again, I'll remind you that pausing these videos are actually very important to your ability to learn. And so it's critical that you actually take some time to try to work through these problems all on your own instead of just watching the answer that I'll provide here in a minute. So please do that right now. All right, welcome back. As with all of our syntheses, what I encourage you to do is to start thinking about what kinds of pieces are present in the starting material and the product. And so I'm just going to zoom in here a little bit. And here we have a really nice benzene ring in our product, and that presumably is going to come from this position as well. That means this carbon has got to be that carbon. And we're going to have to convert that aldehyde functional group into a double bond. And so that's a very important piece of this. Retrosynthetically speaking, we also should be able to recognize that ethers are almost always made from either a halide or from an alcohol. And so if we could convert this to an OH, then we could use the relatively common reagent aldol bromide to make the ether. And I guess that would technically be through the other carbon-oxygen bond. And so we probably want to think that through a little bit. Let me just delete that other arrow here. So that would be a really great place to start thinking retrosynthetically. And I'm just going to scroll down to the bottom so I can put my favorite answer in these boxes up above a little bit later. So let me just do a quick retrosynthesis here then. And we kind of already mentioned that we could go back to this alcohol from the starting materials and aldol bromide. And that would technically be a Williamson ether synthesis. Now from here, we could imagine a couple of different things. Maybe we could imagine going directly back to the aldehyde and a Wittig reaction, because we really do like Wittig reactions. So we can put PPH3 in here, and maybe we can have just an OH group on the Wittig. Turns out this is going to be a problem, and I'll explain why in a minute, but at least it's something that we could consider. Maybe we could consider an aldol reaction, so that would require us to go through the ketone temporarily, and we know how to reduce ketones to alcohols, so that should be okay. That's just a functional group interconversion. And then maybe we can go back to the aldehyde, and in this case, I guess it would be acetone, so that's a very common inexpensive ketone, so we like that. And we could think about other ways how to make a alcohol as well. So one that you might recall from prior chapters is that if you have a alkene, we can hydrate that alkene to make the alcohol. And we could imagine doing that either in a Markovnikov fashion with acidic water or in an anti-Markovnikov fashion using hydroboration oxidation. And here, there is a complication involved, and that is that we actually have a diene system, and that diene, of course, is going to be slightly more difficult to manipulate than a regular old alkene might be. All right, so at least initially we have 3 different retrosyntheses, and this is how synthesis problems also become difficult is, they tend to balloon as you go backwards into more and more options. And so then, for instance, we might have to think about how to make this thing, and, maybe that is where we can use our Wittig reaction. So now maybe we can have our aldehyde, and now we can have our PPH3. And in this case, we would need a 3-carbon containing piece. And this is nice because we could imagine making this instead from PPH3 and aldol bromide. which is the same component that we were going to use up here. So that might be nice. We could get a lot of value perhaps in this problem out of allyl bromide. Now, I mentioned that this reaction was going to be a problem, and the reason for that is you have this leaving group here. So let me just redraw this reagent down below here. And so if I have PH3P, and then I have my double bond OH, there are really two problems with this. And remember, this is a resonance structure of the doubly charged form. So if I have P plus, then I would have C minus OH here. And the first problem that you'd encounter trying to make a reagent like this is that this OH group is going to be quite acidic. And so if you compare the pKa of that OH group, it would be about 16-ish. And if you compare that to the phosphonium salt, it's probably in the low 30s. And so it would be much more likely that a base would deprotonate the OH than it would be the CH to make the ylide in the first place. The other issue, so presumably we could protect the OH and get around that, and so that would be one option. But there's another problem with this reagent, and that is this minus, because it's uphill compared to the OH minus, what this would probably do is just kick off OH minus, and then we would have a different vinyl phosphonium salt. Like this. And now we wouldn't be able to necessarily do a Wittig reaction with this salt. And so there's a couple of problems. So what I'm going to do is encourage us to just axe that pathway to begin with, and we'll be able to come up with two successful pathways, either by approach 1 or approach 2. Now, approach 1 is my favorite because I think it's the simplest to execute, and it uses only the kind of most basic organic reagents. And there aren't any issues of chemoselectivity really in that pathway. So I'm going to put my approach 1 up in the boxes above, and then we'll discuss approach 2 on the page below. So starting from benzaldehyde, what we could do is use NaOH as a base to deprotonate acetone and do an aldol condensation. Now, when we do that, it's important to have excess acetone. If you didn't have excess acetone, you'd end up making a molecule called dibenzylidine acetone, which is this molecule. And it turns out that this is a ligand for palladium. And so you can buy, sometimes it's abbreviated as DBA. So you can buy DBA 3 palladium 2 as a common palladium pre-catalyst. Turns out it's not a great one, but that's a story for a different day. So here, if we have excess acetone, that'll mean that that there's a lot of acetone, and so we won't be able to have 2 benzaldehydes per acetone. And so that should give us the product that we want here. And now we can use sodium borohydride for the reduction. To get the alcohol that we needed. Now, there's something subtle about this ketone. You'll notice that it's an alpha beta unsaturated ketone. So let me just label those here. And those can undergo reduction at the beta position in a conjugate addition manner as well. And so that's often a complication to these sorts of reactions. And for those of you that are true synthesis aficionados, you might know about the Louche reduction. And the Louche reduction is there to avoid issues of beta reduction. And it uses cerium trichloride with sodium borohydride as a reagent combination. That's not critical, and the Louche reduction is definitely not covered in most organic chemistry textbooks. And in this particular example, we probably wouldn't expect too much conjugate reduction anyway, because the product here is conjugated, and that conjugation of the alkene to the benzene ring will help stabilize that alkene, and it'll help make it less electrophilic and less susceptible to conjugate reduction. And so even though that is a concern for those of you that are experts in organic synthesis, for the average organic 1, organic 2 purposes, I would accept just sodium borohydride all on its own for the ketone reduction. So then the last step here would be a Williamson ether synthesis, and we like NaH for our really strong base for that, and then we can use that allyl bromide for the ether formation, and that would get us to our overall product. So, and then we're done. Okay, now I did say that there was a second approach using the hydration of an alkene, and so we can look at that down below. So let's just assume that we forgot about the aldol reaction. We got really fixated on using a Wittig reaction. You can still do that. And so what we like to do is take allyl bromide then and PPH3. And so this will do an SN2 reaction. And by the way, for most synthesis problems, I don't actually expect students to draw the arrows in. I'm just doing it here to help so that you can follow along. And that would get us to this phosphonium salt. And since we have a plus, we need to add a minus since we started with some neutral stuff. And so the bromine is going to be the key intermediate there. We can convert these phosphonium salts to their ylid in the presence of strong base. And so one common base that we like for this is phenyllithium. And I'm drawing phenyllithium here as a covalent bond. But if you're more comfortable with it, you can have lithium plus and phenyl minus. So I'm okay with that as well. And that's just a strong base. And what we're going to end up having here is crashing out lithium bromide as the salt, and then we'll make the ylid as the neutral species. And so we have plus, and I'll just remind us then that we have this kind of dipolar form of the ylid, but there is a resonance structure where these are neutral. So don't be thrown off if I draw it in the double bond form. And I'll just draw in that arrow so that we're comfortable with it. And going the other way, then it would just be this arrow kind of going all the way around back to there. All right, so using that, then we can use our benzaldehyde starting material and complete the Wittig reaction. So that would give us this phenylbutadiene, and that would be a great start potentially. Now we have to consider how to react at alkene 1 instead of alkene 2. And our simplest conditions for reacting at double bonds is just simply H plus and water. And remember, H3O really tends to mean H2SO4, and so usually HSO4 minus is the counter ion to that hydronium for a number of these conditions. So if we take H plus and we could imagine either of these double bonds attacking, so we could imagine that one, and then we could imagine, you know, having protonation at either side of that double bond. So then we could have protonation at this site, could have protonation at this site. We could then invoke the other alkene. Could have protonation at this site, or we could have protonation way out here and have this one. Now, when comparing these, what we should do is think about how stable the carbocations are. And in this one, we have a benzylic carbocation. And in the grand scheme of things, a secondary benzylic carbocation is actually a pretty good one, because remember that alkene electron density in the benzene ring can delocalize, and you can draw a bunch of resonance structures here where we actually spread that positive charge into the phenyl ring. This one is secondary and allylic, and that's also not too bad. It turns out that that's okay. So for those of you that have been through chapters on alkenes or dienes, you probably drew some secondary allylic carbocations in that chapter, so that's all right. This one is going to be real bad because it's primary and it has nothing else going for it. So we definitely want to discontinue any thoughts of that one. Turns out this next one here is going to probably be the best. And so it's secondary, it's allylic, and so that matches this one right next door. But the other thing that's special about it is if we have some resonance structures here, we can actually push now it can be secondary and benzylic, and that makes it the best one overall. And so it picks up the best attributes of both of these, and it ends up being the most conjugated carbocation that we have out there. So that is great. The only hiccup then is if I go back to my black pen here so we can keep it straight. If I react this with water and I react this one with water, I might end up with two different products. So this would be the alcohol that we want. And this would be the alcohol that we might not want. So this would be the wrong isomer. Now, as it turns out, this one is conjugated. This one is not conjugated. And because of that, this one should be the thermodynamic product. And for those of you that have experienced this issue when adding across dienes before, please go back and review kinetic versus thermodynamic products. For the purposes of this, it means that we should be able to get this alkene out if we also add in some heat. So if we just treat this with sulfuric acid under high temperature conditions, we should be able to get any of the kinetic product here to form this molecule, presumably by reprotonating that alcohol, reforming the same carbocation, and then eventually everything will shift down to the more stable conjugated product. So that would get us through where we need to go. And we could then alkylate this OH in the same Williamson ether synthesis we used above with allyl bromide and sodium hydride. So I can do that here. So NaH and allyl bromide would get me to the same product. And so that would be okay there. Now, for those of you that are true aficionados, you might think to yourself, wait a minute, if allyl alcohol is cheap and I could use that instead of water, maybe I can go directly from the diene all the way to the ether. And that should be possible as well, at least in principle. So we should be able to go from here in the presence of allyl alcohol to our desired product, assuming that we put in some H2SO4. The only downside there is allyl alcohol might be able to make allyl cation under those conditions, and allyl cation could conceivably do a Friedel-Crafts reaction on the benzene ring. So that might be a complication. So for all of these issues of complication, not only that, the Wittigs aren't really the most fun reaction to do in the lab because you end up with a lot of PPH3 oxide as the byproduct. My favorite answer to this is the one that I showed way up here above using the Aldol reaction. That being said, if I were grading these on an exam, I would also accept the Wittig reaction, assuming that the students recognized some of these issues about thermodynamic or kinetic products and at least had some description of that in their work below. All right, so that sums up this synthesis problem. Hopefully you're enjoying these videos on the Professor Carbon YouTube channel. As a reminder, if you're interested in a particular problem type, we actually have a playlist for that. And if you're interested in a particular set of content, let's say all about ketones and aldehydes, there's a playlist for that as well. So please go ahead and find those on our channel. Also, we really do appreciate those of you that are becoming YouTube subscribers to the Professor Carbon. That really helps provide some encouragement to keep making these videos. Lastly, if you want access to these PDFs, either in the filled out or the blank version, you can get those on our patron page by becoming a patron subscriber or follower. So with that, thank you for this video. Please share it with one of your friends.